Okay, binding energy is the quantity of energy that must be put into a nucleus in order to break it into its constituent particle. Therefore, binding energy of a nucleus is proportional to the difference between the total mass of the individual nucleon and the mass of the nucleus. The binding energy or energy released during a nuclear reaction is given by the Einstein energy equation, which we have as E equals to mc squared, where E is known as your binding energy, and that should be in joules, and M is the mass defect in kilogram, or it could be in atomic mass unit. 1 atomic mass unit is equivalent to 1.66 times 10 raised power minus 27 kilogram. So AMU simply means atomic mass unit, and mass defect is the mass of original substance in atomic mass unit minus mass of the product in atomic mass unit. Alright, so unit of energy in nuclear reaction can be expressed in unified atomic mass unit, which is this. We call this the unified atomic mass unit, and then it could also be expressed in joules or even the electron volts, and we have the following conversions. One electron volt is equivalent to 1.6 times 10 raised power minus 19 joules. 1 mega electron volt, it is 1.6 times 10 raised power minus 13 joules. Then you have 1 atomic mass unit, which is same thing as 931 mega electron volts, or 1.490 times 10 raised power minus 10 joules. So let's quickly look at some example. 1. In a nuclear reaction, the mass defect is 2 times 10 raised power minus 6 grams. Calculate the energy released given that C, which is the speed of light, is 3 times 10 raised power 8 meters per second. Firstly, here, remember that M has been given to you the mass defect, which is 2 times 10 raised power minus 6 grams. I need to convert the grams to kilogram, and if gram is going to kilogram, whatever you have is to be divided by 1000, or you multiply by 10 raised power minus 3. So you have the M mass equals to 2 times 10 minus 6 times 10 minus 3, and that will give 2 times 10 minus 6 minus 3 minus 9, and that is in kilogram. That is the mass defect. Then the speed of light against C is 3 times 10 raised power 8 meters per second. Then we also calculate the energy. Energy, which is E, is given as mc squared. Therefore, E now will be m is 2 times 10 raised power minus 9 times C is 3 times 10 raised power 8. So here we have 2 times 3, 6, then times 10 C with squared. C squared so that will give me 2 times 10 raised power minus 9 times 3 square will give 3 times 3, 9 times 10, 8 times 2, 16. So 2 times 9 will give 18 times 10 minus 9 plus 16, which is 1, 8, 18 times 10 minus 9 minus 9 plus 16 will give 7. Then move the decimal point once so that will be in standard form. You have 1.8. You move forward, that means 10, 7 plus 1. That gives 1.8 times 10 raised to power 8, and that is in joule. That is the energy. The energy now of the binding energy released during the nuclear reaction is 1.8 times 10 raised to power 8 joules. So we can pick example 2 also, and we have it that in a thermonuclear reaction, in a thermonuclear reaction, the total initial mass is 5.02 times 10 raised power minus 27 kg, and the total final mass is 5.01 times 10 raised power minus 27 kg. The energy released in the process is what? So we have to look for the energy released in the process, but note something has been given here, mass defect has been given, which is initial mass minus the final mass. So you have initial mass minus the final mass of the product. Okay, here initial mass is 5.02 times 10 raised to power minus 27, and the final mass is 5.01 times 10 raised to the power minus 27. Subtract the decimal part, 5.02 minus 5.01, 0.01, then pick times 10 raised to the power minus 27. Put this in standard form, move the decimal point once. That means 1.0 times 10, we move twice, minus 27 plus 2, and that will give 1.0 times 10 raised to the power minus 29, and that will be in kilogram. And the mass now is 1.0 times 10 raised to the power minus 29, and speed of light c is 3 times 10 raised to the power 8 meters per second. Then we have to calculate the energy released during the process. So therefore energy from the Einstein equation is mc squared. So you have E equals to m is the mass defect 1 times 10 raised to the power minus 29, then times speed of light 3 times 10 raised to the power 8 squared, and this will give 1 times 10 raised to the power minus 29 times 3 squared will be 9, then times 10 raised to the power 16. Multiply the whole number. 9 times 1 will give 9 times 10 minus 29 plus 16, and we have 9 times 10 minus 29 plus 16 minus 13 joules. So therefore the energy released during the nuclear reaction is minus 13 joules. Okay, a possible fusion reaction is deuterium plus deuterium to give tritium plus protium with the release of energy, where Q is the energy released as a result of the reaction. If Q is 4.03 mega electron volts, calculate the atomic mass of tritium in atomic mass unit. Now the tritium here is the unknown, so we can say let X be the atomic mass of tritium, which is this, in atomic mass unit mu. So if you look at this, the atomic mass unit for deuterium is given as 2.01410 unified atomic mass unit. Then for protium 1.00783 unified atomic mass unit, and 1 unified atomic mass unit is 931 mega electron volts. So all we need to do is this energy that has been released, the energy for Q, which is 4.03 mega electron volts, will be converted into unified atomic mass unit. And how do we do that? 1 unified atomic mass unit is 931 mega electron volts. Then we have 4.03 mega electron volt for Q. That means X unified atomic mass unit for that Q is equals to 4.03 mega electron volt. If we cross multiply this, multiply this, this multiply this, so you have the, for that unknown, which is X, that is the unified atomic mass unit will be 4.03 mega electron volts over 931 mega electron volt. We are trying to convert the mega electron volt for the energy released, which is energy released that Q. We are trying to convert it to mega electron volts. So energy released now, which is Q now in mega electron volt will be this, cancel this, then 4.03 divided by 931 will give 0.004329 unified atomic mass unit. Now put the value of Q, the value for tritium, protium back to this energy equation which we have here. put it back to all this equation. Anywhere we see 2, mass number 2 and atomic number 1 for hydrogen, we replace it with 2 point this. Anywhere we see mass number 1, atomic number 1 for hydrogen, which is proton, we replace it with this. Then this tritium becomes the unknown. Then Q again, anywhere we see Q, we replace it with the latest value that we add for Q. Then we'll collect the like terms. So that gives 4. The deuterium, now deuterium is 2.01410 plus another deuterium 2.01410 equals to, that means to give tritium, our tritium is the unknown, plus protium, which is 1.00783, then plus Q, which is the energy release now in atomic mass unit, this, and that will be 0.004329. Do the necessary additions. Adding these two together, we have 4.0282. Then we have X plus, when you add the other two together, it gives 1.01216. Collect the like terms. X will be 4.0282 minus 1.01216. That shows that X will now be 3.01604 nil. That is the unified atomic mass unit for the tritium, which is 3H1, is 3.01604 in unified atomic mass unit, not mega electron volt again.